An interval of time must start at one time instant t1 and end at another time instant t2. During such an interval, the x-observer can only find three possible situations regarding the movement. A. The c-axis is motionless until the time instant t2. Or B. The c-axis is moving with acceleration. Or C. The c-axis is moving at velocity of v. Situation A should reject itself because it directly violates the statement velocity v is then imparted to the rod. Acceleration in situation B means no constant velocity and therefore must be disallowed in our study. Situation C is a repetition of the situation in which the word then is serving as a single time instant. Then the analysis leading to the exposure of the invalidity of equation 2-A and 2-B just repeats itself. Further, equation 2 is the source of the idea of length contraction advocated by relativity. In case the word then means a non-zero interval of time, the c-axis moving at v with respect to the x-observer will make him see a scene that at the completion of then, the origins must be deviating from each other by a distance of delta x equals v delta t. Let us arbitrarily choose a point P on the c-axis before any movement happens. With a coordinate value P, point P matches a point on the x-axis that has a coordinate value of xp. As soon as a velocity v is imparted, relativity's length contraction will make the x-observer see the length between P and the origin of the c-axis to be worth the value of L on the x-axis. At t2, with the distance of delta x that the origin of the c-axis has completed, point P should locate itself on the x-axis at a point indicated by equation 5. Subsequently, the location variation of P along the x-axis is indicated by equation 6. This location variation will cause the observer to conclude a speed for the movement of P as shown by equation 7. Speed Vp is obviously different from v, which is the speed of the origin of the c-axis. Let us choose another point, Q, on the c-axis. Similar to deriving equation 7, we can arrive at equation 8 for the movement of Q. Unless m equals 1, speeds Vp and Vq are not equal to each other. These two speeds in turn are not equal to v, since every particle point on the c-axis would move at speed different from each other. Relativity thus destroys its requirement on the rigidity of an inertial system. Since Q can be arbitrarily large on a numerical axis, relativity must allow the appearance of infinite value for speed. The existence of a speed limit in nature is thus found crumbled.